Hello everyone, welcome. For this problem, we were asked to solve the following differential equation using the substitution method for homogeneous equations. The quantity x squared plus y squared times dx plus 2xy times dy is equal to 0. Before getting into the solution procedure for this problem, we want to discuss what it means for a differential equation to be homogeneous. A homogeneous differential equation satisfies the following test for homogeneity. If we were to express the rate of change dy dx as a function of x and y, replacing x with tx and y with ty must yield the same original function of x and y, which means replacing x with tx and y with ty does not change dy dx. This essentially means that for an equation to be homogeneous, the presence of the variable t does not influence the equation at all. Homogeneity is advantageous because it allows us to rearrange our differential equation in a way that allows for a convenient substitution that helps us arrive at a solution to the problem. In order to test our differential equation for homogeneity, the first step is to express dy dx explicitly as a function of x and y. This is done with some simple algebra, and we end up with the following. The next step is to replace the x's with tx and y's with ty. Next, we could perform some simplifications and rearrangements, and we see that all of the t's cancel out, leaving the original differential equation unchanged. This means our differential equation is indeed homogeneous since it passes the test for homogeneity. Now, what is the advantage of dealing with a homogeneous differential equation? Well, the advantage is, for a homogeneous equation, the function of dy dx can be manipulated and expressed as a new function g that is only a function of the ratio y over x and no other standalone x's or y's. Because we already know that our equation is homogeneous, it must mean that we should be able to rearrange the right-hand side and write it only as a function of the ratio y over x. We see that splitting the fraction, canceling out common factors, pulling out the 1/2, and flipping the first fraction gets us to this point. We see that we've transformed the right-hand side, which was a function of x and y, to a new function, g, which is only a function of the ratio y over x. And again, this is only possible since our original equation was homogeneous. What we're going to do now is redefine this ratio as v and substitute v in for every occurrence of y over x as such. We see now that we have a differential equation in terms of 3 variables, y, x, and v, and it seems like we've added an extra variable v, so in order to maintain 2 variables in our system, we can now write y in terms of v and x and substitute this into our original equation. So we still only have an ordinary differential equation with 2 variables. But before we can finish this step, it appears that we do not only need y, rather we need the derivative of y with respect to x. So we could simply take the derivative of the equation of y in terms of v and x, and after applying product rule, where the derivative of x with respect to x is just 1, we end up with the following. We can now substitute this into our equation for dy dx, and we end up with the following transformed differential equation. We see here that we've transformed our system from having an input of x and an output of y to having an input of still x, but an output of v instead. The other important and convenient fact about this new transformed ordinary differential equation is that it is separable. At this point, we can move all v's over to the right-hand side and combine them into a single quotient by creating common denominators. We do this because having all of the v's in a single term will make it easier to find the integral. After this, we can move the x and the dx to the right-hand side, and all v's and dv to the left-hand side, and then proceed with integrating both sides. Starting with the right-hand side, the integral of dx over x is simply the natural logarithm of the absolute value of x plus the integration constant c. On the left-hand side, it seems like we can carry out a u substitution, where u is equal to 1 plus 3 times v squared. That means that du dv is equal to 6v, which means that dv must equal du over 6v. After substituting in u and dv back into the right-hand side of our equation, we could cancel out the v's and make some simplifications, which results in the following. Here again, we have the integral of du over u, which is simply the natural logarithm of the absolute value of u. The constant of integration can be thought to be absorbed by the constant on the right-hand side. We can now substitute u back into our equation, and let's not forget, u is in terms of v, which we defined as y over x. Substituting v back into our equation to bring it back to the y and x domain results in the following. On the left-hand side, if we look at what's inside of the absolute value, y squared and x squared will never be negative, which means 1 plus 3 times y squared over x squared will also never be negative, which means that we could simply replace the absolute value symbols with parentheses since there's no scenario where the absolute value will actually affect the expression inside of it. We can continue simplifying both sides by moving the 3 over to the right-hand side, applying rules of logarithms, and raising everything to be the exponent of the base b. Again, applying rules of exponents, we can separate the two terms in the exponents into the product of 2e's raised to each term, resulting in the following. Here again, we're dealing with the absolute value of x, which can either be equal to positive or negative x, depending on what's needed to maintain that the absolute value of x is positive. We can replace this with a plus minus sign signifying any sign change that may or may not occur. The plus minus sign along with the e to the 3c can all be thought of as a single constant, which we could simply call k. Now we could simply solve for y using some basic algebra, and we end up with the following. If we want, we can express our solution in a more compact form by writing it as a single quotient by creating a common denominator and combining terms. After doing this, we end up with the following final solution to the original homogeneous differential equation.